Hello and welcome to COP 4708. So far, we know by looking at the Excel sheets, reports, and forms of a company or organization to identify the entity or entities that organization would like to track. The forms and reports will include the required information about each entity, which are called attributes. One of these attributes will be the determinant of other attributes. Others might be candidate, but a specific one will be the determinant for all of them. To identify the relationships between attributes, we use what's called functional dependencies. Also, we learned how to identify the different relationships between entities. For example, the many-to-many relationship, many students who are taking many courses, and the mandatory to optional relationship. After that, we developed a model or a blueprint to represent the database that we have and their relation. In this session, we will learn how to transform the data model that has been created into an actual database design. Now remember that in the model you can do changes. Once you are in the design stage, you don't want to change anything. You just want to implement at that point. So this stage where you fix all the different aspects or changes for the model and try to make it a final decision for the design. So what are the steps of transforming the data model into a database design? The transformation consists of three main steps. First, replacing the entities and attributes with tables and columns. If you remember, we said an entity is at the end will be a table, and the attributes or fields are the columns. Then we replace the identifiers with keys, especially the one that can identify or determine the rest of the attributes, which we will call the primary key. We specify the column properties and verify normalization. Then we will create relationships by placing foreign keys, strong or ID dependent or mixed or subtype or recursive, specifying the logic for enforcing minimum cardinality and establishing the relationship between these entities. Based on the information that we studied before in the previous sessions, you will know that we will change the student entity, in this case to a student table, and we will use the student ID as a primary key. You can see the symbol of the key designated by that symbol. We know that this is the primary key for that table. And of course, you can see the functional dependencies at the top here, where student ID as a primary key can actually determine the rest of the information for the student, and the rest of the information is being used as attributes which being created, in this case in the design, as columns. In case that we don't have information enough or a unique determinant, we said that we can create a surrogate key that meets the ideal requirements, but might have no meaning for the users. It does have a meaning for the administrator that created them, the surrogate key, which will represent the different entities or the instant of this entity. Also, we can specify the candidate keys, all alternative keys that might be used in that table. Remember that the candidate keys are alternative identifiers of unique rows in a table. Email could be a candidate key, but still, usually you don't use that as the primary, although, in some cases, you can go to some of the stores, retail stores, or you can call a company, and on the phone they will tell you, okay, what's your email address, and based on the email address they can pull your information. If you go to a retail store like Best Buy and you don't have your information, then you can tell them, or you don't have your card, you can tell them your phone number, and they can pull your information based on your phone number. So they can use different candidate keys to pull the information, but mainly you have one unique identifier that can be used as the primary key. And then we have certain notations that we are going to use for those alternative keys, where we can say AK, alternative key, NM, where N is the number of the alternate keys and M is the column number in that alternate key. So we can identify these candidate keys within the table once it's been created. And this is an example of identifying the alternative keys. So for a social security number, we said that it's an alternative key, and that's number 1, and then the email is number 2. Now remember that the N is the number of the alternate key, and M is the column number in that alternate key. So it can be considered as alternate key number 1, and M is the first column or second column based on the information that we have. One of the other things that we need to specify in this stage is the value. Are you going to allow people to enter a value or enter a 0 or leave that field empty? If you are going to allow them, then you have to add the word null in front of them, or choose null. Null will allow leaving the information empty. In other words, it will be optional. And that's how, when you go to a web address trying to fill the information for maybe billing or shipping information, you will find some of the information are optional and other fields are mandatory. The optional can be identified by the word null, and the mandatory can be identified by the word not null. That means you are required to fill information in that field. You are required to fill information. So now we specify the column, the different columns. Again, let's start with the entity. We identified the entity, which was converted into a table, the attributes that was converted into columns, the primary key, the identifier, which was converted into a primary key. Then we have alternative keys. Now we are talking about the value that will be inside there are we allowed to leave it empty or we have to fill it, and that is a null and not null property, or actually can be considered as constraint. So we are putting a constraint on optional or mandatory filling information. Also, we need to identify data type. What type of information you are allowing to enter there. For example, if you put number, then if you try to put any text in that field, it will be rejected. So you have to be specific on what you are allowing as a data type in that field. The different data types that you might see is a character or variable character. It can be a date format, it can be a time format, it can be money or currency, it can be integer, it can be decimal. And you will see other data types, and that's one of them. Things that we saw in different database management system like Access, where they have data types, and we can learn from that the different data types that's allowed for a field or to enter in a field of a table. This is a list of the different allowed data types for SQL Server. You will find some of them different in Oracle or in DB2, but most likely they are almost the same. They are common, they have the same, maybe they will change some of these types, or they will name it differently, or join it, or separate it, but at the end it will be or it will mean the same. For example, if you have it money, if you have it currency, if you have it financial, whatever the name is, you know that it's related to money. If you have it numbers or numeric, you will know that it's related to numbers, and so on. So those are the list, and you can look at the different data types in different database management system, compare them, and learn more about how to do that. And this is some of the data types in Oracle, and you can see they are using the character, they are using the binary. In the SQL Server, it's binary. Here it's BLOB, which is binary large object. And then date for the SQL Server, they have the date and time, they have the date here, and so on. So you can compare the way you can compare these database management systems. Just take a look at the different data types on the internet, or if you have a book, look at the difference and see how it can be created in each database management system. One of the things that we are allowed to do is to identify a default value for that column. So instead of us entering the same value again and again, then we can identify a default value that will be entered automatically. If change is needed, then you can allow that change to happen, but always you will have the default filled in that cell, and after that you can change it. Those are some of the examples that you might see. For a perishable item, you might be P, you might have the word P uploaded to the column, imported I, one of O, otherwise N, and so on. So you can actually fill in the cell the default value that you would like based on the attributes or the properties of that value or that column. When creating the database, we need also to consider rules, policies. So I have to put some constraints, limitation on data values or data types and so on. The constraints are for different types. We have domain constraints, we have range constraints, we have intra-relation constraints, and inter-relation constraints. For the domain constraints, the column value must be in a given set of specific values, so you will not allow to put any value that's not mentioned in that range or in that domain. The same for the range constraints. So the domain and range are almost the same. With the range, we have a range of sequence of numbers or values, while for the domain you can specify names, set of specific values or specific names to fill in that space. For the interrelation constraints, the column values are limited by comparison to values in other columns in the same table. You cannot do values that's different from one place to another. You can do the same if you have two tables, and you can compare the two columns or different columns in two tables and make sure that they are the same. And the reason for that, you want to make sure if you do an update for column in table 1 is being reflected in the same column name in table 2. Now remember that we are creating relationship to connect these tables, and I'm putting the foreign key in the other table. So you want to make sure if you change the primary key number in table number 1, it will be reflected as a foreign key in table number 2. The same number has been changed. So any updates will be reflected in all tables, so you don't have to worry about going to each table individually and making that update. And this is what we call referential integrity constraints. During the design, you will verify normalization, and we did actually, by going step by step on looking at the different entities that we have in the system and creating functional dependencies, then breaking in those entities into pieces with the attributes and the types, the properties for each attribute or for each column. Then actually we are using the BCNF or the 4NF, the normal forms that we learned in chapter 3. So we are normalizing, but also you need to verify that you are normalizing your tables and making sure that they are in the proper format needed for the design. Then we start creating the relationships. The one-to-one relationship, strong entity relationship, where we place the key of the first table in the second table as a foreign key, or the other way around. In either design, it will work. Whether you put the foreign key from this one in this one or this one in this one, it will work. It should work without a problem. Parent-child or child-parent, it should work. The most important thing is not to forget to put the primary key as a foreign key in the other. This is an example of the foreign key where you have here the primary key in the first table, the primary key in the first table is member number, which was used as a foreign key in the second table. or I can use the primary key in the second table as a foreign key in the first table. So whether you do it like this or the other way around from table 2 to table 1, it should be the same. The other relation is the one-to-many, where you place the primary key of the table on the one side of the relationship into the table on the many side of the relationship as the foreign key. The one side is the parent table and the many side is the child table. So place the key of the parent in the child table, This is an example where we have company and department. Then you will see that you need to put the company name as a foreign key in the department table. For the many-to-many, in a many-to-many strong entity relationship, there is no place for the foreign key in either table. So where can we put the primary key or the foreign key, the relation? How can we create the relation? If it's many-to-many, and we have company, which has it may supply many parts, and the part may be supplied by many companies. So we will be confused because the company name will be different each time for the same part. Maybe the same part can be brought from company A and company B and company C at the same time. So how can we do that? In this case, we create intersection table that can store data about the corresponding rows from each entity. The mission of the intersection table is to connect those two tables with the information that's being repeated or that has redundant information. So each table's primary key can become a foreign key linking back to that original table. And this is an example. So we have the company name, and the part number, and we can use those two primary keys as foreign keys in the new table. Both of these keys will make a composite primary key for the new table. Composite primary key. Relationship using the ID dependent entities. We can do it with the many-to-many, which is what we just discussed, and we can do it through association. We can do through the multi-value attributes. We can do through the archetype instance relationship. So an intersection table holds the relationship between two strong entities in a many-to-many relationship. It will contain only the primary key of the two entities as a composite primary key, as we said before, which they were actually foreign keys coming from the main table. The association table has all the characteristics of the intersection table. They are the same, but it's adding one more column of attributes specific to the association of the other two entities. What do I need to associate, or what do I need as an attribute or a field or a column that can be added to represent the new entity? For example, in this case, what will be the price? If I'm buying the same item from different companies, 3 different companies, what will be the price from each company? I would like to know so I can compare the different companies and see which one will be used as supplier. Or maybe I have to bring that part from 3 different companies, because one single company will not have the amount that I need at a certain point. If I have a multi-value attribute, remember that we talked about that in the modeling and before, where we addressed the need for a table that will be separate to address the many phone numbers that might be used for contact information in a company. In this case, if we have even more than one contact person, then I can also create another table just for contact person. So either by phone, the phone contact or contact phone for that person, or the person himself, his name, I can create new multi-value tables or attributes. For the archetype, for example, the class with a section, we have sections like each class has 3 or 4 sections. For example, the math. In the math department, they have the math 1033. They have almost 36 sections, maybe more, I don't know. But having all these sections will make them create an archetype instance pattern between the class and the section, and they can use actually the primary key of the main entity or the parent entity as a part of the composite key in the child entity. And I can add, if I need to add the foreign key as attribute, and the composite key, change that into just one primary key that I will call it reference number. So here we use the composite of the two names, the class name and the section number, while in this case, in this design, I change that into one primary key that I call the reference number, but so as not to forget, I use the section number and the class name as foreign keys coming from the other classes or the other entities. In the mixed entity pattern, as you remember, we did this model. We created that model that will connect the customer, salesperson, sales order, item, and the order line item. We can now just transform that into a database design as follows. So this is the database design. What we did for each entity, it's been transformed into a table. Each identifier being transformed into a primary key, and then we have the attributes for each entity, or the fields, in this case the columns for each table. Then we have the different relationship that we created, and in this case we have the line item pattern relationship with a mixed entity definition. The same we did with the employee and skill. We created a mixed entity relationship, and we can do it. We can transform the model into design as shown in this slide, or as we can see in this slide, as shown in this slide. Another example for a relationship, the subtype relationship, the employee, the manager. The manager, we said that either exclude or include database management. We can make the database manager or the database admin separate from the manager, or we can make the manager as a database as the same as database admin. He will be the manager and the database admin. So this is the subtype relationship. The recursive relationship, this is the model, and this is the design. Recursive relationship for the one-to-many employee and managers. This is the model, and this is the design. As you can see, we don't have a lot of change between the model and the design, except that we have to identify the primary key, add a foreign key so we can connect, and then you will have the relationship which will be almost the same, or it is the same. Then we have the many-to-many recursive relationship. And the ternary relationship must constrain. The must constrain requires that one entity must be combined with another entity in the ternary or higher order relationship. And then must not constrain requires that certain combination of two entities are not allowed to occur in the ternary or higher order relationship. And must cover constrain a binary relationship specific or specifies all combination of two entities that must appear in the ternary or higher education or higher order relationship. This is an example of the must constraint, where we have the binary must. In this case, if you compare the salesperson, we have 10, 20, and 30, and for the customer number we have 1,000, 2,000, 3,000. So if we look at the must constraint, then since I have here 2,000 and I have constraints that were related to the table before, the customer table, then looking at the 2,000, only 20 is allowed to be here. So now the constraint forced only one number. If I put 10, it will give me an error. If I put 30, it will give me an error. And that will force the integrity between these tables, the relationship integrity between these tables. Must not constrain. Again, if we look at the 2000 here, we can see that the 2000 can be 20, can be 45, but it cannot be any other number. So for the 2000, we cannot repeat these two numbers because it's already been used. So 20, 45 cannot appear here, but any other number might appear. Must cover constraint. If we have repair table, task table, and we have the auto repair table, the repair number 10, 20, 30, 40, and we have the task number, certain tasks assigned to repair number 10, others to 20, others to 30, and others to 40. So we have a constraint that must cover these numbers. So if I have here 20, then this should be the repair number, or the task number should be in the 2000 task numbers. If I put 3001, then it's not accurate. If I put 4,000, it's not accurate. If I put 1,000, it's not accurate. Since this is a repair number of 20, then the task number must be in the 2000, and the next number will be 2002. In addition to the maximum cardinality and the relationship between the tables, we were looking at the minimum cardinality, which forces you to think about the optional and mandatory between the child and the parent. So we have the relationship of optional between both the parents and the child. We have the mandatory to optional between the parent and the child. We have optional to mandatory, optional for the parent, mandatory for the child, and we have both mandatory for the parent and the child. For the optional, no action is needed in that relationship. For the other relations, there are some restriction on inserting or updating and deleting the activities. This table will show you the required actions when you have the parent as required, and this table, and the second table will tell you the actions required when the child is mandatory. So this is if the parent mandatory, this is if the child mandatory, and those are the action required for the parent. Those are the action required for the child when you create such a relation. So during the design, looking at the minimum cardinality, we know that for the optional for both the parent and the child, there is nothing to do. For the mandatory to optional, then we are forced to use the first table, which is the mandatory actions for the parent. For the optional to mandatory, we are forced to use the mandatory actions for the child. And for mandatory, we are forced to use both tables for the parent and the child as mandatory actions for both of them. This will be all for chapter 6. If you look at the end of that chapter, you will see how they transformed the university model that we worked on the last session into design. Look at that, look at the different relationship and see how it's being transformed. And again, all what you need to understand in this session is how to transform the data model that's been created in the previous chapter into a database design that will be implemented later on as a code into the database management system. If you have any questions, you can email it to me or call, and that will be all for this session. Thank you.